Morning and welcome again to Maths with Mr. Courage, and today we are dealing with differentiation, one of my best aspects that is calculus. And by the way, differentiation is a very important aspect where we are mainly dealing with the derivative of a function, and it relates to the gradient of a tangent at any specific point. But today we are looking at the rules for differentiation. And on our last series, we also looked at differentiation from the first principles, which looked quite longer. And today we are looking at the shorter version of differentiating given functions. Right. First of all, we have the standard rule. If f of x is equal to ax to the power n, then f prime of x, that is the first derivative, is equal to a multiplied by n x to the power n minus 1. What happens is you drop the power, you multiply by a, and then you subtract 1 on the power. Now this is just a basic notation. We can also represent the same f of x as our y is equal to a x to the power n. Then when we use this, we will say therefore dy over dx is equal to a x and then n minus 1. This is notation number 2. The other one can be given as follows. The derivative with respect to x of a x to the power n is equal to a dot x multiplied by n to the power n minus 1. So these are three different notations, but all the same, we are all differentiating with respect to x. So there's a lot of respect in differentiation, so we are going to follow that order. But not only this, we also have to take note that each time we are differentiating a constant, if f of x is equal to a, that is a constant, our derivative will be f prime of x is equal to 0. It might look complicated at the beginning, but we are going to break it down, making use of a basic polynomial. For instance, find f prime of x if f of x is equal to 3x to the power 3 minus 4x squared plus 5x minus 6. This is a cubic function, and we can still differentiate it now applying the basic rule of differentiation, and then we go our f prime of x is equal to, when we drop the power there, it becomes 3 times 3, this is 9, x to the power 2, we have subtracted the 1, and then on the next one, minus 4 times 2 gives us minus 8, x to the power 2 minus 1, it's 1, and then the next one, it will be plus 5. This is power 1, so 5 times 1 is 5, 1 minus 1 is 0, so x to the power 0 is equal to 1. Then minus 6 becomes a constant, therefore the derivative of a constant is equal to 0. This is our first derivative. Now what does this function represent? It represents the gradient of a tangent. This is the gradient of a tangent at any given point. At any given point. For instance, if we are to evaluate f prime of 2 will be equal to 9 brackets, we substitute our 2 squared minus 8 multiplied by 2 and then plus 5, which will be equal to 2 to the power 2, that is 4 times 9, that is 36, minus 16, and then plus 5. 36 minus 16, that gives us 20, and then plus 5, we get 25. Therefore, the gradient of the curve at the point where x is equal to 2 will be equal to 5. In other words, if you are to reverse back to the complex functions that you were differentiating from first principles, you can take note that you can still find the direct derivative using the rules. So from now on, when you are differentiating, you are no longer applying the first principles, but you are now applying the rules. That is very, very important. And also take note, there are specific rules that are also applied, and I'm going to mention them as follows. There is a stage that we call preparing to differentiate. You prepare, and I'll explain what it means. Before differentiating the different pieces, 1, 2, 3, 4, these are 5 different parts or 5 terms. From your grade 9, you could classify that. You must make sure that you prepare to differentiate. What does it mean? In as much as you might have this term in a position where it can be differentiated, but if the second one is not ready to be differentiated, you have to prepare. I will give an example. If f of x is equal to x squared minus 1 over x plus the square root of x. This looks a bit complicated because it's not in the standard form ax to the power n. So there's something that should be done. This has to be dealt with as well as that. So this is the stage of preparing to differentiate. So we are going to keep the function as it is on hold. All these other functions, for instance, this part x to the power 2, it stays the same, or we don't change it until all these parts are also done. Now in this case, we will have our f of x is equal to x squared, and then this one, from the laws of exponents, it becomes minus 1 x to the power negative 1, and then this one becomes plus x to the power half. In other words, we are now seeing the laws of exponents being used in preparing to differentiate. Now at this stage, we now have ax to the power n, ax to the power n, ax to the power n. Now the function is ready to be differentiated. Only then we can now write, therefore, our f prime of x is equal to this one, 2x, and then this one minus 1 times 1, this gives us positive 1. So plus 1 x to the power negative 2, this is minus 1 minus 1, that is negative 2. And then here plus 1 over 2 x to the power. Normally when you deal with fractions, you can even write 1 over 2 minus 1. This is going to give you negative 1 over 2. If they are more complex, you can even write the stages as you go down. Now in most instances, we are encouraged to leave our answer with positive exponents, which means our f prime of x will be equal to 2x and then plus 1 over x squared, and then plus 1 over 2 and then x to the power and 1 over 2 x to the power half. This is very, very important, the stage of preparing. Now, which other aspects are very important? I'm going to mention them that are used in preparing. We might have number 1, we might need to expand. We might need to expand a certain function if brackets are involved. Number 2, we might need to factorize. Number 3, and here, before I forget on factorization, take note of the cubic expression when you factorize x to the power 3 minus y to the power 3. You learned this in grade 10. It's very, very important in factorization as well. Then the other one, obviously we have looked at the laws of exponents. They are also used in preparing to differentiate. And then also we have got basic fractions. The use of fractions is also very important in differentiating. Then the next one, we can also have a splitting process which is connected to fractions. Number 5, we can just note it as splitting the fraction. And then number 6, this one is very important. We can note that we can use the change of subjects of the formula. change of subject. In other words, we might have a function that is involving x and y, but we have to change the subject so that we can either differentiate with respect to x or with respect to y. And then on a higher order, we might have to use the chain rule in differentiating. But for now, this is the basics of differentiating, and we make use of the rules, and then step by step we get to apply. And then lastly, why are we doing all this differentiating part? We said initially in order to find the gradient of a tangent. Why do we need this gradient of a tangent? We are interested in this equation of the tangent. It's very important. In some instances, we can even go to the extent of the equation of the normal. And then also, this function that we are differentiating is connected to the basics of the turning points when we sketch the graphs, that is the minimum point or the maximum turning point. So this process is also very important. It helps us in curve sketching because we cannot sketch a cubic function if we don't know the turning points. So at every turning point, we have to find the derivative and then we do the equation to zero. We will look at that in the next series. But so far, this is the foundations of differentiating. Then there are some scary numbers that you might see, especially on the constant. Let's say we are differentiating f of x, which is equal to, for instance, pi root 4. This is a basic number, this one. So its derivative is also equal to 0. Why is it a constant? The expression does not have anything to do with x here. So the same way we see a number that is 5, this is exactly the same way we see the pi. So it's a temptation to see this as a variable. So this is also a constant. And lastly, on the laws of exponents, I need to emphasize this one. Let's say we have, I'll write it here, 1 over 2 to the power 1 over 2 root x, or let me say 1 over 2x, right? X squared, yeah, it's fine. Now when you look at this, during the process of preparing, we are taking only the x squared to the top. So you might be tempted to take even the 2. We only take this x squared alone. In other words, it becomes 1 over 2, and then here when you take to the top, it becomes what? X to the power negative what? 2. You'll see this one a lot. In some instances, it can be 1 over 2 root x also. 1 over 2 root x. It means this one is only the problem. It should go to the top. This fraction 1 over 2 is okay. So these are some of the nitty-gritties that you need to check when you do differentiating from the basic rules. So for now, we are going to pause there. This is our basic introduction, but now we need to apply in differentiating different functions. We are going to make use of the lower order and the higher order questions from the practice activities. But for now, let's take a short break. Thank you.